tangent planes and normal lines. We will focus first on the concept of tangent planes, how to find the equation of a tangent plane, and then secondly we will look at how to find the set of symmetric normal lines to the so-called surface. Well, we first begin by considering the function z equal to f of xy, where z is set to be a surface. And then from there we develop the concept of forming z in relationship to small f by subtracting z on both sides, and we look at capital F, this capital F function representing the surface for us, where the center is said to be focused, going from the center to the surface. The vector thrust is outward, with here f of xy minus z. To go the other way around, then the force would be moving toward the center. So here they say because f of xy minus z equal to 0, you can consider S to be the level surface of f given by capital F of x, y, z equal to 0, and we call this an alternative equation form for the surface. Here's just a pictorial illustration of what's going on. You have this this capital F function. What you notice is that you have this vector there that we haven't claimed what it is yet, but that's going to be the gradient of f. And indeed, it's perpendicular. The gradient is perpendicular to the level. We say to the level curve. So here is perpendicular to capital F. The definition of the tangent plane and the so-called normal line: let f be a differentiable function at the point P on some surface S given by the capital F of x, y, z equal to 0. And hopefully that the gradient does not zero out. The gradient of f at that particular point is not 0. So the plane through P that is normal to the gradient is called the tangent plane to S at P. And then the line through P having the direction of the gradient of f is called the normal line to S at P. Now, first of all, my emphasis is to build the equation of the tangent plane. So to find this equation of the tangent plane to S at some fixed point x naught, y naught, z naught, let x, y, z be some arbitrary point in the tangent plane. Then we can build the vector v here to equal to x minus x naught I plus y minus y naught j plus z minus z naught k. This vector is said to lie in the tangent plane. Now, when you consider that the gradient function is normal to the tangent plane, and so we have, if you think about it, perpendicularity, and when two vectors are perpendicular or orthogonal, their dot products are equal to 0. So if that be the case, then we can build this equation. Well, let's see how that's done. So if you consider a surface, surface S, and here we have some vector F, and then this point here will be the point x naught, y naught, z naught. Then if you take the gradient, so the gradient of f is said to be perpendicular to the function. We are looking for the equation of the tangent plane that is lying within the plane of this gradient. So let me see if I can change the color. Now, I want to note here this point. This is the point x naught, y naught, and z naught. Sorry about that. Telephone. So what we will do here is to pick some arbitrary vector that they call here the x, y, z, and form this vector v in relationship to this fixed point. And there, change the color. This guy here is perpendicular to this gradient, and so we're in this tangent plane. And so if that be the case, then we say that the gradient of f here evaluated at the point x naught, y naught, z naught is perpendicular to this vector v, and so the dot product is 0. So now if you think about that, this gradient vector has the form capital F, take the partial derivative there, and just use my shorthand if you will, comma the partial of f with respect to y, comma the partial of f with respect to z. It's dot product with x minus x naught comma y minus y naught comma z minus z naught is equal to 0. So we fashion that out. We have the partial of f with respect to x. Go ahead and just put the point that it's been evaluated on. So this is x naught, y naught, z naught times x minus x naught plus just taking the inner product plus the partial of f with respect to y at x naught, y naught, z naught times y minus y naught plus the partial of f with respect to z evaluated at that fixed point x naught, y naught, z naught times z minus z naught is equal to 0. Well, this, my friends, gives you, sorry for writing slanted, this is the equation of the tangent plane. And so that's how it's built here. Well, let's see if we can consider some of the problems there. So here, in this problem, find the equation of the tangent plane to the surface at the given point. So we first have to write little f in terms of capital F of x, y, z. So this is x naught, x squared minus 2xy plus y squared. Remember that z is set to equal to little f of xy. So this is minus z, or minus the f of xy. So the partial of f with respect to x is 2x minus 2y. The partial of f with respect to y is minus 2x plus 2y. And the partial of f with respect to z is negative 1. Now we can calculate these partials at the point here. X naught, Y naught, Z naught is 1, 2, 1. So this becomes 2 minus 4, or negative 2. You evaluate this partial at the point 1, 2, 1. This is negative 2 times 1, so that's negative 2. Then this is plus 2 times 2, or 4. And this gives us positive 2. And to evaluate this partial at the point, well, this partial is fixed. So we forever there get negative 1. Now with that, to build the equation that you want, and if you recall back from algebra that these partial derivatives, really they're just the direction numbers for the vector. So x is said to move toward negative 2, y is said to move toward 2, and the z is said to move toward negative 1. And so we build based on the formula. This is f, the partial f with respect to x, times x minus 1 plus the partial of f with respect to y times y minus 2 plus the partial of f with respect to z times z minus 1. That's equal to 0. We put those direction numbers in, negative 2, 2, and negative 1. And so that gives us negative 2 times x minus 1 plus 2 times y minus 2 minus 1 times z minus 1 equal to 0. Now we simplify that. So that gives us negative 2x plus 2 plus 2y minus 4 minus z plus 1 equal to 0. And then we can write this as negative 2x plus 2y minus z. Let's get the numbers on the other side. So this is 2 minus 4 is negative 2 plus 1 is negative 1 on the left side, and so it becomes a positive 1 on the right side. And then just multiplying through by a negative, you can clean that up. This is 2x minus 2y plus z is equal to negative 1. Okay. Well, do the same thing for this problem. So the partial of f with respect to x is 2x. And, you know, we're writing capital F of x, y, z. Here, this is simply x squared. Most of everything you want is already on the left side, plus z squared minus 36 equal to 0. Partial of f with respect to y is 8y. The partial of f with respect to z is 2z. We plug in the numbers. So here, this implies that the partial of f with respect to x evaluated at 2, negative 2, 4 is equal to 2 times 2. So that gives us 4. Evaluate this partial at the point 2, negative 2, 4. So that gives us 8 times negative 2. So we get negative 16. Evaluate the 2z at the point 2, negative 2, and 4. So this gives us 2 times 4. We get 8. So now we plug everything in that we want. This is 4 times x minus 2 minus 16 times y minus a negative 2 becomes y plus 2, then plus 8 times z minus 4 is equal to 0. Since I have common numbers 4, 16, and 8, I'm going to just divide both sides by 4 just to try to make the math a little bit easy for me. So x minus 2 minus 4 times y plus 2 times z minus 8 is equal to 0. Simplify that. X minus 2 minus 4y minus 8 plus 2z minus 16 equal to 0. And so here we have x minus 4y plus 2z. Let's see what we have. This is minus 10, and minus 6 is negative 26. Add that to both sides, and we get positive 26. And that looks to be the equation that you want. And I believe those numbers look to be right. So next we'll look at the symmetric lines to the normal.